my talk is going to be about the effect of climate change and actually increasing environmental temperatures on human physiology and health. And first of all, I was asked to give a bit of an overview of kind of how I got to where I am now in my academic career. So going from the present to the past, right now, I'm a postdoctoral researcher at Maastricht University, and I work in the group of Professor Wouter van Marken-Lichtenbelt, who some of you might know also in the context of the discovery of active brown adipose tissue in the adult human body. But yeah, in our group, in our research group, we call it lovingly the thermu. We deal with all kinds of, it's short for thermoregulation and metabolism actually of Maastricht University. We deal with all kinds of the whole spectrum of human thermoregulation, really from shivering physiology up to exposure to heat. We look at energy metabolism and all kinds of environmental factors, not just temperature, but also, for example, light, and how all of that is connected to health. So, and how did I end up in this group? Actually, already during my master's internship quite some time ago now, I did a project in this group, and then after that was invited to do my PhD there as well. And my PhD was around the topic of humans and warm environments, which fits really nicely with the topic of this conference. And I looked at physiology, health and behavior of human beings in warm environments. So if you're interested in maybe getting a digital copy of my doctoral thesis, you can do so on my ResearchGate, or if you just Google the title, you will be probably prompted to some kind of download site where you can get it. And because I've just attended the career symposium as well, or career path symposium, I just want to say, yes, I have been already at Maastricht University for quite some time. I'm actually German, so and I still live in Germany, but I work in the Netherlands, so that is kind of already some international experience for me for some time. But I just want to, it was never planned like this. I never planned to be at one university for such a long time, but it just happened because it's a really nice place. We have great research facilities, and it was just basically by chance. So you don't necessarily need to go to different places or different universities for every step of your career. It can also just be different, as in my case, it was by chance. Okay, but now let's talk a little bit about this great research that we're doing at Maastricht University. And to give you a bit of an overview of what I'm going to talk about. So first of all, I will talk about climate change and the built environment, and why that I'm going to tell you in a second. Then I'll talk about climate change in humans, passive heat acclimation in humans, and then I'll conclude and hopefully give you a few take-home messages that might be helpful. So, first of all, why the built environment? You might think this is not an architectural conference or for civil engineers, this is for physiologists, but why is the built environment so important for us? I just want to give you a short poll. So Rosie, if you could launch the poll, that would be great at this point in time, to ask you, what do you think? Hang on, I don't know if you can see it, but yeah, let me know if everybody can see it. So what do you think on average, how much time in a day do people spend inside buildings? And this is now specified for the UK, but actually this is true for most developed countries in the world, or industrialized countries. Do you think it's less than 50%, approximately 22 hours a day, around 75%, or approximately 16 hours a day? And I'll give you another 3 seconds now to vote, so I'll count down. 3, 2, 1, and Rosie, would you please share the results with us? Okay, wow. So a lot of people, actually 24 and 24 people voted between 22 hours a day or around 75%. And let me show you what it is. It is actually 90% of our time. And even more so if you also add the time that we spend in cars or in in other closed enclosures in vehicles. So you can see that indoor environment has a tremendous importance for our health and well-being because we spend so much time there. We spend so much time in the indoor environment. So yeah, this is why you can guess that it makes a big impact on us. Okay, let's see. So we have heard probably a lot during this conference on how the temperature is changing. So I'm not going to repeat a lot of that, but I just picked one very interesting fact. So it has been projected that in 2050, a summer in London will be around 6 degrees Celsius warmer than it is now. So, well, for some that might sound like horrible. For others, it might sound nice, because if you look at it from a geographical point of view, it would mean that London would move approximately 650 miles or 1,000 kilometers further south, and then would actually be somewhere around where Marseille is now at the French Riviera. That sounds nice, but actually there will be lots of extreme weather events in the future. Heat waves, as we have seen in the last decade, quite a lot of them, and also previously, of course, will be more frequent and more intense. And I think if you approximately 30 years or younger, you have never in your life experienced a cooler than average month in your life. So this is really interesting, I think, to realize. So we hit new records pretty much not just every year, but oftentimes every month. Things are just heating up much more quickly. And the problem is we are not really prepared for these kind of climate challenges. Houses are overheating, not just in the UK, but also in lots of other places, because they're not built and they're not designed for these kind of climate challenges. They're overheating even in a mild summer. So if we look at what a building at the French Riviera, a traditional building, would actually look like, it might look something like this. So you can see it's a structure with very thick stone walls, small windows, light colors. And if we move a little bit further south and we look at, actually is another nice example at Santorini, you can see very clearly these houses are built in a certain way. They are light colors to reflect the sunlight, thick structures to kind of balance out the variation of temperature during the day. And you know, all in an old building with thick walls, it's oftentimes much cooler inside than outside. And often also these places, these buildings have shutters that people from their experience would keep closed during the day to keep the heat out, and then in the evening open them up to let the air circulate and let fresh air in. So this is really nice, but what do buildings over here look like? They look oftentimes lots like this. There's lots of glass. We nowadays not just build these kind of public buildings or office buildings in this way, but also new build homes and with a near airtight envelope. So basically, if you don't open a window, no air comes in and no air goes out. They're highly insulated for the reason that we want to conserve the temperature inside, which is nice during a cold winter. But in summer, it actually, it just gives the building a big risk of overheating. And since everything is increasingly warming up, this is a big problem. Lots of buildings are dependent on air conditioning because no natural ventilation is actually possible. You can't even open a window in some of these buildings. And this means there's a high energy demand. So if you imagine this beautiful building in London downtown, if you imagined a power outage, it would be, just imagine 35 degrees Celsius outside, this building would be uninhabitable pretty quickly. So this is difficult. And on top of that, we have something called the heat island effect. So in densely populated cities, because of so many buildings in one place, heat accumulates. And in many buildings, we use air conditionings these days in these public huge office buildings, which makes the problem even worse because hot air is actually blown into the city because you want to keep it cold inside, but then it heats up more outside. So you basically come into into a vicious circle. And I just want to point out, so this is London. You can see quite a hot heat island. And about here is Richmond Park, where our friends from the University of Roehampton work. So in London, you guys probably have the coolest head in summer. So yes, from a human perspective, why should we actually bother? Because we are tropical animals. Humans are naked, we can sweat, and we very well adapted to withstand heat. So looking at climate change from a thermoregulation perspective, should we actually bother? And to know what is hot for us, it might be a good idea to look at the thermoneutral zone quickly. And Dr. Emily Watkins has pointed out yesterday that I was going to talk about it, so I'll briefly do that, although it was not the plan initially. But the human thermoneutral zone is, per definition, the zone in which we can still thermoregulate only by using vasoconstriction and vasodilation. So where we only use the blood pump basically to the periphery and to the core to regulate our body temperature. If it gets cooler, so if temperature decreases, at some point you will need to increase your metabolism, either by, for example, brown adipose tissue or shivering, to keep yourself warm and to keep your core stable. And there's two different definitions for the upper critical temperature, and one is has to do with sweating, and one has to do with heat-related thermogenesis. So when the metabolism increases because of, for example, an increase of heart rate or the Q10 effect. Because I don't want to dwell on this long, because I have to move on for time reasons, I just want to tell you, if you're interested in the thermoneutral zone, go and read up some of these literature references I have cited here. And just so you know, this is highly individual. Every individual has a different thermoneutral zone, so it's basically impossible to say this is the temperature of the thermoneutral zone or this is the temperature range. Okay, but let's look further. Human heat acclimation. So if the temperatures are increasing, we need to adapt to this. What do we know about heat acclimation? Most studies available have looked at extreme heat acclimation, active heat acclimation, so with exercise in the heat, because the scientific community is interested in preparing the military and athletes for events such as, for example, Tokyo, that is now 2021, which is projected to be really warm for lots of athletes. So how can we prepare our athletes to withstand these temperatures and to perform well? And lots of studies have looked at that. What are the possibilities to acclimatize athletes to heat? And we see that it doesn't really matter what kind of a heat acclimation protocol we use, but there's a few parameters that generally do go in the same direction. So you see core body temperature decreases if you let somebody, for example, cycle in a hot environment for a couple of days. You train somebody in a hot environment, you will see that core body temperature decreases. At the same moment, performance will increase, so it will be easier for people to exercise in the heat, and sweating will be more effective. However, what about what we just talked about? What about our everyday life situations where we are sitting in a sedentary mode in our overheated office or at home, or we go on a holiday in a warm country? This mild and passive heat stimulus, as opposed to the active and extreme heat stimulus that I just talked about, what do we know about this? Do we actually acclimatize as well? And information is lacking. So because the scientific community just focused on these active studies much more. There is a little bit of information, but then it's usually connected to hot water bathing or such, but not to ambient temperature as we are sitting in usually. So we came up with a study where we wanted to look at that. And the research question was, what is the effect of increased ambient temperature on our physiology? And we thought probably we're going to see some kind of acclimatization or acclimation effect here as well. To quickly look at the methods. So it was 11 lean young men that participated in the study. for normal BMI. And what we did was we acclimatized them for 7 days for 4 to 6 hours. So they came to the lab, they didn't sleep there, but they just came during the day. They were sitting in a room with 33 degrees Celsius environmental temperature. And before and after, we performed a heat stress test, and we call it the UP protocol. So here it's called UP because basically we start at a thermoneutral temperature, and then temperature increases slowly up until approximately 40 degrees Celsius. And we measured lots of different things. This is what it looked like for a participant in the setup. We measured blood perfusion with the laser Doppler with the laser Doppler flow metry system to see what the blood perfusion does. We measured energy expenditure with indirect calorimetry, so we measured oxygen consumption and CO2 production. We measured core temperature with a telemetric pill and heart rate as well with an equivital device. We measured skin temperature at 26 different sites of the body. We measured blood pressure, and also we measured sweating by just measuring, by just weighing people before and after and see how much water they lost or how much weight. Okay, let's go and look at the results. What happened? So yes, we see even with the passive and mild stimulus as the 33 degrees Celsius for 6 hours, 7 days in a row, we do see an acclimatization, an acclimation effect. I shouldn't say acclimatization. We see an acclimation effect. So you see here that these gray squares are over the whole UP protocol are lower than before acclimation. So we see that this classical heat acclimation parameter really changed through our intervention. We also see a redistribution of skin temperature. So basically, after acclimation, even in the baseline condition, even during thermoneutral temperatures, people were more readily pumping blood to their extremities and kind of anticipating that they were going to get this heat stimulus, so they needed to lose heat. So you really see that blood is more shifted to the extremities to lose heat. We also, because of that, because with vasodilation, the peripheral resistance is lower. So we also saw a decrease of blood pressure, also in the thermoneutral and in the heat. And because of that, because of, people were already losing heat more readily and the core temperature was lower, creating a thermoregulatory buffer, so people were not overheating as fast, people had to sweat less. So we see a decrease of sweat loss during this protocol. So we look at what our results, and we see indeed this mild and passively induced stimulus induces physiological changes, which is good news. So we see that we can actually acclimatize or acclimate to these temperatures, and we have an increased resilience to heat. So we accepted this hypothesis, worked out. But this was a young population, so young people, healthy. What about more vulnerable populations? So for example, people of older age, people that are overweight, people with impaired glucose metabolism, because this is a population, obviously, or this is a big group of our general population. Demographics are shifting to people are becoming more older, and so this is really relevant to look at. And we found a sample that is actually exactly, so the research question was, what is the effect of increased temperature on thermophysiology, and this time also glucose metabolism in an overweight, middle-aged population, and also here we had men. And you might think, why glucose metabolism? Well, we thought that glucose metabolism would improve because there have been a few studies looking at the effect of heat on glucose metabolism. And they were all done with hot water baths. So again, it's a different mode of heating somebody up or a different kind of situation. But quite a few studies have looked at it now and see that heat can be beneficial for glucose metabolism. And so yeah, this is why we thought this might happen here as well with our relatively mild situation. Okay, so we found a group of people that were overweight and middle-aged, and also had a slightly increased fasting glucose. So this 6.0 is not yet pre-diabetic, obviously also not diabetic, but this group of middle-aged men was clearly at risk for developing metabolic issues. Yes. And what we did was very similar to the first study. This time we let people acclimate for 10 days, and 35 degrees Celsius is slightly more intense than with the first group, but we really wanted to see what happened. 4 to 6 hours per day again, and we performed again the same exact protocol as during the first study. And now, on top of that, before and after, we also looked at blood samples. We wanted to look at the glucose metabolism. We wanted to see if this mild acclimation protocol would also lead to a change in glucose metabolism. And we used a technique called hyperinsulinemic euglycemic clamp, which is the gold standard for insulin sensitivity measurement. So yeah, this is what we used. And to give you a bit of an impression, this is what it looked like. On the left-hand side, you see a participant during the up protocol, very similar as the first picture I just showed you, just from a different perspective, but also the measurements we did were similar or the same as the first study in the young man. And now in the right-hand side picture, you can see somebody sitting in this climate chamber that we have at Maastricht University. So people were really sitting there for 6 hours and doing some office work or reading a book. This is what it looked like. And looking at the results. Again, also in this group, we see that core temperature decreased. So again, also here we see the gray squares throughout the whole up protocol were lower than the round circles. So after heat acclimation, people had a lower core temperature again. But we did not see a change in skin temperature redistribution. So basically, we did not see, as in the first group, that much more blood was pumped already to the extremities. This effect was diminished in this population. We also see that blood pressure decreased, slightly less pronounced than in the first group, but it's actually quite nice because heat has also been previously suggested to be an interesting alternative prevention strategy or therapy strategy to look at for example, hypertension or cardiovascular disease. So this kind of confirms that again, that it might be a nice thing to look at our heat. And we saw that there was no change in sweat loss, because you can see obviously core temperature decreased, but we did not see the change in skin temperature, the shift to the skin. So people were not able to really lose as much heat as in the young group. So they still need their sweat to really keep their core temperature or to keep their temperature stable to go against the heat. And what we also see nicely, also in this heat acclimation study, people were benefiting from the heat in terms of glucose and insulin. So we took fasting samples, again, before and after acclimation of plasma and glucose, and the concentrations were lower in both cases. So that's great to see. Plus, on top of that, we looked at endogenous glucose production. So that's basically the glucose that is produced by the liver. And yeah, in a pre-diabetic situation, that is usually a little bit increased. So it is nice to see that here, after heat acclimation, endogenous glucose production was lower, both in a baseline state, so in a fasted state, but also when stimulated with insulin. So this suggests that the liver metabolism actually is improved after heat acclimation. And we're looking into this further at this moment. So to conclude, passive mild heat acclimation actually elicits beneficial physiological changes. So good news, we adapt to the heat. it improves our resilience to the heat, but it is highly individual and it varies among populations. In terms of health effects, it might be nice to look at using heat indeed to improve cardiometabolic health, and we're looking into the underlying mechanisms more at the moment to figure out what is it actually that makes heat beneficial. So also here we can say hypothesis accepted, even though in the second group the acclimation effect was a little bit less pronounced. So, but now looking at, okay, we can adapt, but for whom can heat still be dangerous? And we know that heat waves bring along excess deaths. The majority of victims is older than 65 years because of their decreased capacity to lose heat via the skin, which others have shown previously. And also we see this in our passive heat acclimation study. There's also reduced sweat gland output, so people can can dissipate heat less efficiently with increasing age, especially if they already have pre-existing cardiovascular problems. This makes the risk even more serious. And we can say the fitter the better. So if somebody is very fit, even in older age, this makes the risk a little bit less, but it doesn't take it away that age still makes a difference in the ability to lose heat via the skin and via sweat glands. So how to beat the heat? Well, we as the Thermu group, our research group is really of the belief, not just belief because we also prove it with data obviously, but we just want to say it's very important to actually become more resilient. If you sit in a nice office building, as I showed earlier, and you have the air conditioning on 21 degrees Celsius and you have a heat wave in summer, you will go out and you will really get a kind of a heat shock because you're just not used to it. So decrease these 90%, spend time outdoors or decrease your air conditioning. Let yourself get used to the temperature that you're exposed to, which is also kind of natural. I mean, the temperature that you find outside. But also think about hot baths or sauna, which is all possible measures to improve resilience to heat and to become more acclimated. And on top of that, obviously, it's always a good idea to maintain good cardiovascular fitness. And with older age, this will also improve the ability to cope with heat. And obviously, not the mean temperature is dangerous, but the extremes. So if things get 6 degrees warmer on average, that's probably still okay. But you know, if it really gets extreme during heat waves, it's important to protect yourself from exposure to direct sun, to radiation, seek shade, drink water, be hydrated, and do all these things that are important to kind of protect yourself from these extreme thermal conditions. And with that, I would like to thank you very much for your kind attention. I don't see anybody, so I don't know who's actually there, so this is a little bit weird. But thank you very much, and I want to thank everybody who helped me performing these studies. I want to thank my lovely research group and obviously all funding bodies for making this possible. Thank you very much, and I'm happy to take any questions.
Perfect. Thank you, Hannah, for a really fascinating presentation. Just will remind everybody that it's the e-poster session is starting now. So if you've signed up for those, please do go join those. But for those who are interested in sticking around, we will answer some questions anyways. Yeah, so I'll just look at the Q&As here, and I see there's been a few upvoted. So the first one is the air coming from air conditioners dangerous to us? And how different is it from the natural air, and which do you recommend we should be having?
Okay, so I'm not an air condition specialist, so I can't say really in terms of, I don't know, chemical substances, etc., that are filtered or not filtered. But what I can talk about it from a thermoregulation perspective. So sometimes you would recognize that in summer I don't know, you walk towards your workplace and then you already have in your backpack, although it's 30 degrees outside, you have a thick sweater because you know inside it's gonna be cold, and this damn air conditioned, sorry for my French, but it will always give you 21 degrees Celsius. So it is really unnatural. You come from the heat outdoors and you sit basically in a temperature that that is very different, that is cold, and different from the outdoor conditions. And yeah, so this will not help you to acclimatize. This will not help you to naturally, which is actually acclimatization. And what I talked about previously is if you induce it artificially, then you call it acclimation. So sorry for the confusion. But if you want to acclimatize yourself naturally, then reduce the air temperature, the air conditioning unit a little bit, and allow yourself to really be exposed to the natural thermal environment. Maybe open a window. Maybe sweat a little bit. It's not an issue.
Thank you. There's a nice question here asking about gender differences in heat acclimation. Do you have any insight on that?
That's very interesting. So unfortunately, both studies that I did were in men. I would have liked to also include women, and yeah, I will definitely do that with my future studies. I think that the general direction will be similar. So I think that also women will readily acclimatize to heat or acclimate to heat. But we know that women can deal with heat a little bit better sometimes than men. So if you look at thermosensation, so if you look at putting a man and a woman, we all know that in 21 degrees Celsius, usually the women would feel cold and the man would say, well, it's totally neutral for me, so I don't know what the problem is. And this has to do with metabolic rate, for example. Women have on average a lower metabolic rate than men. So for them, warmer temperatures are actually more comfortable, and they can deal with them up until a certain degree better than men. So yes, there are certainly differences in the starting point as well, but I think the general direction will be similar between sexes.
Great, that's really interesting. We have another question from Jem Chang from McMaster University. And they say, thank you, Dr. Pallubinsky, such an interesting talk. Can you please speak to how you came up with the acclimation parameters, for instance, hours per day or ambient temperature used, and how the physiological changes you observed compare to changes seen after more extreme heat acclimation protocols? And finally, did you measure thermal perception or anecdotally, how did your participants tolerate the heat acclimation?
Okay, yeah, if you could just leave the question up so that I can read a little bit again. Yeah, okay, thank you. So thank you, Jem. The temperatures. So yes, as I introduced, I have always kind of worked at the intersection between the indoor environment and human physiology. So what we wanted to achieve with these acclimation studies was really to look at what would it be like during a heat wave in an overheated office. And 33 degrees is something, or 35 degrees is something that is oftentimes the reality in a building in summer. So we really wanted to see where the starting point was of this presentation as well. If buildings are overheating, how do as humans, how do we cope with that? So this is how we came up with, for example, the 6 hours. Obviously, people are in a building, for example, to go to work, maybe a little bit more than that, maybe 8 hours, but we thought it might be a good starting point, and it was also realistic for our participants to come over to the university for this time. And then obviously you also leave the building again and you go home, and maybe it's different there. So this was kind of the timing. And the temperature, as I said, was just realistic for a heat wave in a building, what we expect at this point in time, not in 50 years from now. Then let me see. Yeah, so how does it compare with changes after more extreme heat acclimation protocols? In general, it's just more pronounced. The body is, in German we have a saying, I don't know if that exists in English as well, but a good horse always jumps only as high as it has to. So the body really does the same. It just acclimatizes to whatever it's exposed to. You have the same with training in sports. I mean, you know, if you train for 10-kilometer run, you won't be able, because you trained for a 10 kilometer, you won't be able to run a marathon just because of, maybe you will be, but it will be difficult. So the body really adapts to whatever it finds and whatever it's repeatedly exposed to. So you see that in more extreme heat acclimation protocols, things will be more pronounced. And yeah, so this is, I think, what I would say. And finally, thermoperception. How did participants tolerate? Yes, so we measured thermal sensation and thermal comfort as well during the heat acclimation and also during the UP protocol. And in general, people tolerated it quite okay. So the 33 and 35 degrees Celsius in a room, yeah, they were fine with it, really. Obviously, they started sweating a little bit after a meal because they were also eating in the heat. They would tell us that they were feeling warmer than before, because obviously then you get the digestive thermogenesis as well that comes on top of it. But in general, they were fine. And you can't really compare this in an indoor situation, oftentimes with an outdoor setting where you also get radiation from the sun. So this is really, this definitely makes a difference. But in general, people were tolerating it quite well.
Thank you for that. Maybe we'll just go through a few quick ones now. We're getting a little bit late in time here. But the next one being, does the thermoneutral zone vary dependent on the individual's natural climate?
Absolutely, yes. I mean, to a certain extent, there's definitely limits to the human body. But if you, we just saw, if you acclimatized or acclimated to certain thermal conditions, your core temperature even changes. And that would also probably shift your thermoneutral zone a little bit. For example, as I just said, gender, sex, if you're a man, you usually have a higher metabolic rate than a woman because of higher muscle mass, and therefore you have a higher, just based on metabolic rate. This changes also your thermoneutral zone. And then obviously looking at also BMI, or stuff like that definitely affects the thermoneutral zone. So yes.
Maybe related this to about where people live, there's a question about, do you think there's a relationship between hot environments that are within healthy limits and things like boosting of your immune system?
Sorry, can you repeat that? I couldn't read it with you. But...
yeah, so do you think there's a relationship between people who live in hot environments within a healthy limit and things like boosting the immune system? So, health benefits from living in hot environments. Yeah, so
that's an interesting question, and I don't think I can really answer that because I'm not really an immunologist or virologist or so. So also in terms of looking at COVID, for example, I don't know if the heat would boost your immune system or not. I'm sorry, I can't answer that. What I can say is obviously people think always if it gets colder, you get a cold. What we also really literally say like that. But it's not necessarily the cold that makes you ill. It is more how your nasal tract, etc., reacts to the cold, and it makes it more susceptible. For example, also by dry air makes it more susceptible for attacks by bacteria, etc. So it's not the cold necessarily itself.
Okay, maybe just one last one by Helen Hanstock at Mid-Sweden University. She says, hi, Hannah, thanks for a really interesting talk. I wonder, when interpreting your different results in your two studies with regard to skin temperature and sweat loss, to what extent might body composition explain these observations?
Yeah, also an interesting remark. That's also something we thought about. Obviously, our second group had a higher BMI, and thus a higher subcutaneous fat layer. And it has been shown previously that in terms of heat, the fat layer doesn't really make such a big difference. So it's not that just because somebody has more adipose tissue, they would be less able to thermoregulate in the heat. So it's a little bit questionable. I think there's quite a scientific discussion going on about the effect of, definitely in humans. I think in other animals it's very different, but in humans, how much the thicker subcutaneous adipose tissue layer kind of attenuates the possibility or diminishes the possibility to tolerate heat. But yeah, it might still have impacted, but I think the much more important variable I would think is probably age.